The Bohr atom and its astonishing success at describing the interaction of light and matter provides a wonderful starting point for our consideration of chemistry and chemical elements. But first, I think we should explore in a bit more detail the strange physical world of the atomic and the subatomic realm. One of the most profound discoveries of the 20th century is that energy, mass, and other properties at the subatomic scale are quantized. And at that scale, it is impossible to measure the state of a particle without changing the particle in the process. In this lecture on quantum mechanics, I have three main objectives. First, I want to introduce the concept of quanta, the tiny discrete bundles of energy and of matter of which the universe is made. Then I'm going to tell you about the uncertainty associated with making any measurement at the subatomic scale. And finally, we're going to look at the very strange phenomenon of wave-particle duality. Take a deep breath, because this is amazing stuff. And you should leave some of your preconceptions behind when you think about quantum mechanics. The study of motions at the scale of quantum jumps is called quantum mechanics. Before entering this atomic realm, it's really best to forget your preconceptions, forget how the world behaves in your everyday life, because we've never experienced the world ourselves at this atomic and subatomic scale. However things happen around us at everyday speeds, at everyday masses, at everyday scales, may not be at all relevant, and so we have to keep an open mind. And that's what physicists of the early 20th century did. The first odd fact you have to accept about the universe at the atomic scale is that every measurable quantity comes in discrete units, bundles called quanta. The idea of the quanta was first proposed by the German physicist Max Planck, who lived from 1858 to 1947. Planck's career, perhaps more than that of any other scientist, exemplifies, it reflects this phenomenal transition in physics from the realm of classical physics of the late 19th century to modern physics of the early 20th century. He began his work squarely in the realm of classical physics. He studied electricity, he studied magnetism, he studied thermodynamics. But by the early 20th century, he had defined the core principle of quantum mechanics, and he basically defined a whole new way of describing the physical world. Max Planck was a gifted child. He was gifted in both music as a pianist and in mathematics, and for a long time he was unsure what he wanted to do with his life. It's said that he sought the advice of a professional musician. He asked him, "What should I do? Should I be a musician? Should I be a physicist, or what?" And he was told, "If you have to ask, you'd better study something other than music." Well, so he chose math, but he remained an avid amateur musician for his entire life. By his mid-20s, Planck had received a professorship at the University of Kiel, where he offered a variety of advanced courses in the then groundbreaking fields of electromagnetism and thermodynamics of the most advanced sort. In other words, he applied his mathematical abilities to theoretical physics. It might surprise you to learn that at that time, theoretical physics was considered a second-rate science. It was really marginalized in spite of the important contributions it was making. And it's been suggested by some historians of science that this is because the field was dominated by Jewish mathematicians. And there was so much prejudice against the religion that it spilled over into the whole development of physics as a field. Nevertheless, theoretical physics did grow steadily in importance, and in 1888, Planck received a prestigious position as the professor at the University of Berlin and director of the Institute of Theoretical Physicists in Berlin. It was there that Planck did his greatest work. This included an explanation of the photoelectric effect, for which he won the 1918 Nobel Prize in Physics. I want to tell you about that extremely important piece of work on the photoelectric effect. This was a piece of research that culminated in 1900. Planck began this work to explain the spectrum of electromagnetic radiation that was emitted from what's called a black body. An ideal black body absorbs all electromagnetic radiation. It's sort of like your black top on a summer day. But the laws of thermodynamics require that that energy then be re-radiated out into the surroundings, because you have to have a conservation of energy. So you can't just keep soaking up energy and soaking up energy and soaking up energy. You have to re-radiate some of the energy out. And Black body radiation is the nature of that radiation that's re-radiated out. It was the spectrum of this radiation that concerned physicists in the late 19th century. Classical theory, which deals with energy as a continuum of wavelengths, a continuum of energies, can't explain the observed spectrum. It drastically overestimates the amount of energy that would be radiated at very short wavelengths. See, as you go to shorter and shorter wavelengths, you go to higher and higher energies. And even though the total amount of radiation in those shorter wavelengths was less, if you had even a little bit of the very highest radiation, gamma rays and X-rays, for example, that would be much, much more energy coming out of the black body that was going into it. And yet, classical theories seem to suggest you'd have to have a lot of these higher energy types of wavelengths. So what was going on? To solve the problem, Planck suggested that energy comes in discontinuous steps, or in quanta. Now, this is some decades before Niels Bohr and his model of the atom. So this is the first idea about energy coming in discrete steps. The energy corresponds to different wavelengths, or discrete frequencies of electromagnetic radiation. The energy carried by one electromagnetic wave is given by the wave's frequency times a constant, and that constant is now known as Planck's constant. So you have the equation energy equals h, Planck's constant, times nu, or the frequency. With this formulation, Planck was able to match the observed black body behavior of all sorts of objects for the first time. But it required that very bizarre assumption of quantized energy, quantized wavelengths. Few physicists at the time were ready to accept this strange, this abstract idea. After all, energy in everyday situations occurs in a continuum. It doesn't occur in discrete steps. It doesn't occur in quanta. Albert Einstein was able to reinforce Planck's position. This is in 1905 in one of those 4 great papers that Einstein published in that year. This is a paper on the photoelectric effect. This is by which light can eject electrons from certain materials. This is the effect that's used in batteries and solar batteries. It's used in solar panels. And you've probably seen photovoltaic materials. Sometimes they come in little panels, sometimes they come in very large ones. You see them on the tops of houses or by the sides of roads where you have solar energy. And what happens is this. A photoelectric material absorbs a photon, and that actually knocks an electron out of the material so it can flow as an electric current. If you shine a bright light on a photoelectric material, electrons are ejected and they become an electric current in effect. What's strange is that the velocities of these ejected electrons are independent of the light's intensity. Think about that. Force equals mass times acceleration. So if you increase the force you press on something, you're going to increase the acceleration. So the idea of more light intensity, you think you get higher and higher velocities of electrons coming out, but that's not what happens. You can increase the intensity of light shining on a photovoltaic. The velocity of the electron stays exactly the same, just the number of electrons increases. So you double the intensity, you double the number of electrons that are flowing out. But velocities do increase if you use shorter wavelengths. That is, if you go from red light to blue light, the velocity of the electrons increases accordingly because blue light is shorter wavelength that's higher energy. So it's the energy of the wavelength, not the intensity of the light, that determines the velocity of the electrons that are kicked out of that photovoltaic. Einstein adopted Planck's postulate, that is, that light waves carry energy h times nu. And he showed that the kinetic energy of the electrons matched exactly the Planck energy that's contained in the light. Conservation of energy. But you had to assume quantum behavior at this scale. And then the Bohr atom, introduced in 1913, that elaborated on this whole idea of quantized atoms and quantized energy levels. It now appears that many, many different atomic scale properties are quantized. Think about all these quantized properties, many of which you've heard about. Mass comes in quanta. You have individual particles. You have an electron. You have a proton. You have a neutron. You never have half an electron. You never have pi protons, for example, discrete units of mass. And we've seen that energy is quantized into discrete bundles, into photons, for example. Similarly, electromagnetic radiation, all the photons that are representing different quantum leaps in atoms, one photon being produced each time an electron jumps from one level to another. You don't have half a photon. You don't have fractional photons. Electric charge, that also comes in integral increments. An electron has -1 charge. A proton has +1 charge. You don't have some arbitrary fraction of electrical charge. Other atomic properties, including magnetic spin, magnetic field, all different sorts of properties are quantized. Under most circumstances, these quantum effects don't have any influence at all on our macroscopic world. We experience mass and electric charge, energy, other parameters as continuums because we're dealing with so many atoms, so many quanta at once, that we don't generally see these individual sorts of effects. It's only in very unusual situations like the day glow materials I showed you in the last lecture or fluorescent bulbs where you may get an inkling. In lasers is another good example where you may get an inkling that there might be some quantum effect. Most of the time, the quanta don't really matter to us. But at the level of the atom and the subatomic level, they're vitally important. The quantization of the atomic world carries with it the remarkable property that every measurement must change the object that's being measured. I want you to think about that. You can't measure something without changing it while you're measuring it. Every measurement at every scale requires three things, and I don't care if this is the atomic scale or in the scale of entire globes when you do seismology type research. You have to have three things to do a measurement. First of all, you have to have a sample. You have to have a piece of matter. It can be a single electron. It can be an entire galaxy. It can be the Earth. You have to have a sample. Then you have to have a source of energy. That source can be light, it can be heat, it can be kinetic energy. But you have to do something to interact with that sample, and you can't interact with a sample without having some kind of energy in the process. A detector, then, is the third thing you need. You need to be able to detect the interaction of matter and the electromagnetic radiation or the heat or whatever source of energy you're using. So three things are required in every measurement you make. Let me give you a few examples of this. When you look through a microscope, you have a source of light, usually coming up from below. You have a sample that you're looking at, and then your eye becomes the detector, or maybe a piece of photographic film becomes the detector. Similarly, when you look at a star through a telescope, the star is the sample. It's producing its own energy source. That energy is coming to us in the form of electromagnetic radiation, and then your eye or a photographic plate or some other kind of detector is used to detect those photons. When police set up a speed trap, here's a good example. Your car is the sample. The police are using a form of energy that is radar microwaves that bounce off your car, and then they have a detector. The detector measures the interaction between the microwaves in your car, and that tells them how fast you're going. And of course, if you have a radar detector in your car, then you've flipped that whole thing around and you're detecting them hopefully before they detect you. When you go to the grocery store, you do this kind of measurement all the time. You see, this doesn't have to be a sophisticated scientific laboratory. For example, you go to the grocery store and you want to buy a piece of fruit. You want to buy a melon, and what do? You take the melon. That's your sample. You're trying to decide its physical properties. Is this the melon you want to buy? So you might smell the melon, you might tap on it and listen to it. You've got to apply energy to the sample, and you have to have a detector which then will determine the interaction of the energy with the sample. And that gives you information about the object you're trying to study. It happens all the time in our day-to-day lives. It also happens at the largest scale of the most expensive laboratories in the world. For example, the giant particle accelerators that physicists use. These are devices that can cost billions of dollars. It's the exact same thing, though. You have a sample. That's subatomic particles. You have a source of energy, magnetic fields that accelerate those particles in circular motions to huge velocities, close to the speed of light. And then you collide the particles together, you release that energy, and you have detectors that look at the spray of particles that measure the energetic collisions of those particles. The exact same thing as studying a melon in the grocery store or a police radar detector or looking at a sample in a microscope. In principle, every measurement is the same way. In any lab anywhere in the world, you could go into that laboratory and carry 4 cans of paint with you. If you carried these 4 cans of paint, you could paint everything in the laboratory color-coded according to 4 different operations. You'd have one set of paint, let's say blue paint, and you could use that to paint everything that prepares the sample or it controls the environment of the sample, a sample chamber, a vacuum chamber, or a heater or something like that, that just treats the sample. And then you could use red to show everything that produces the energy source, an X-ray beam or a laser beam. Maybe it would be a beam of electrons in an electron microscope, but that would be your source of energy that interacts with the sample. Then you could use yellow to show the detector, and the detector might be an electronic device, it might be photographic material or something like that, but you could paint part of the laboratory yellow. And then finally, you need a fourth color, at least in modern laboratories. That would be, say, green, and that would be for all the computers that store the data and collect the data and process the data, because it turns out that in modern laboratories, that becomes an essential part. And a lot of modern laboratories are devoted to these devices that store data and collect it and process it. But it's really not that different from going to the grocery store, is it? I want you to think about this measurement process and what would happen at the scale of an atom. That's the smallest increment of energy that you can possibly have as a photon, which, if it interacts with an atom, has to change the state of the atom. Let me say that again. The smallest increment of energy you can imagine is a photon, a single wavelength of light, a single piece of light that hits an atom. If the atom absorbs that photon, if it interacts with a photon, you have to somehow change the atom in the process. This situation is rather analogous to trying to find a bowling ball in an empty, dark room. You know, someplace in an empty, dark room, there's a bowling ball. And the only way that you have of finding that bowling ball is taking a second bowling ball and rolling it into the room and listening for the clunk. Well, you could do that. You could roll bowling ball after bowling ball into the room. You might hear a clunk from time to time, but the trouble is, once you located the bowling ball, you'd have no idea where it was after the measurement, because the very process of measuring the bowling ball moves it. Another way of saying this is one of my favorite ways that I learned from Jim Treffel, my colleague, is that you have a car in a dark tunnel, and you're trying to decide where the car is in that dark tunnel. And the only thing you can do is send remotely another car into the tunnel and wait to hear the crash. Well, you can find out if the car is in the tunnel and how far in the tunnel it used to be, but the car is going to be changed after you do the measurement. That's sort of analogous to what happens at the atomic scale. German physicist Werner Heisenberg, who lived from 1901 to 1976, expressed this dilemma, this quantum scale dilemma, in an elegant mathematical form. This expression is known as the Heisenberg uncertainty principle. Heisenberg's storied career began in 1923 with a PhD at the University of Munich. He was given professorships first at the University of Leipzig and then at the University of Berlin. And eventually he was made director of the Max Planck Institute for Physics in Munich. Heisenberg's great insight was the realization you can't know the exact position and the exact velocity of an object in the subatomic realm at exactly the same time. In fact, the uncertainty in position, he said, times the uncertainty in velocity must be greater than Planck's constant divided by the mass, and that can be expressed as an equation. The uncertainty in position, sometimes called delta position, times the uncertainty in velocity, or delta velocity, must be greater than Planck's constant h divided by mass. Well, if the mass is large, the uncertainty in position and velocity are going to be small, because the mass is the denominator of that whole that fraction. But if you have a very small mass, like an electron weighs only 9 times 10 to the minus 31 kilograms. And if you want to know the position of that electron, you want to say that electron is in an atom, and an atom's only about 10 to the minus 10th meters across. You plug those numbers into the constant, and then you see something very, very different indeed. You know the position, so what's the uncertainty in velocity? Well, you just plug in Planck's constant, 6.63 times 10 to the minus 34th joule seconds. You plug in the mass of the electron, 9 times 10 to the minus 31 kilograms, and the distance. You know that the electron's within the atom, that's 10 to the minus 10th meters. And what you come out with is that the uncertainty in velocity is about 7 times 10 to the 6th. That's 7 million meters per second uncertainty in the velocity. 7 million meters per second is a very, very large uncertainty. So you can know either the position or the velocity to any arbitrary precision. But the more you pin down one, the better you know the position, the less you know about velocity, or the more you know about the velocity, the less you know about the position. For a large object like a baseball, this isn't a problem because the mass is so large it swamps all the other effects. But for an electron, it introduces very, very large uncertainties in what we can know about the subatomic world. The uncertainty principle means we can't talk about the quantum world in an absolute deterministic way. We instead have to use probabilities and use a probabilistic treatment of any quantum scale event. This need to resort to probabilities profoundly disturbed Albert Einstein. It's one of the reasons why he really didn't like quantum mechanics. He once said to Niels Bohr, quote, "I can't believe that God plays dice with the universe." To which Bohr replied, "Albert, stop telling God what to do." Given the huge number of electrons that we normally have to deal with, probabilities work exceptionally well. They work in electronics, for example, in ways that allow us to design all sorts of computers and other electronic gear. When solving the probability functions for electrons, and indeed you can describe electrons in terms of probability waves, they're called, physicists quickly saw that the solution to these complex equations could take the form either of a particle-like object or of a wave-like object. This led to a fundamental question: what exactly does an electron look like? One way to differentiate between particles and waves is to see how they behave when you throw them or direct them at a parallel pair of narrow slits. If you have two vertical slits. So when solid particles like ping pong balls are directed at this pair of slits, they go through first slit, or they go through the second slit, or they bounce back right at you. So you have only three possibilities. You go through one slit or the other. And so if you did this for a whole long period of time, throwing ping pong balls at two slits, you'd end up with two piles of balls on the opposite side of the barrier at which you were throwing the ping pong balls. But when waves of sound or water are directed at two slits, two parallel slits, they create what's called an interference pattern with many maxima and minima at the opposite side of the slits, a whole interference pattern. Well, this experiment has been tried many, many times with electrons. When you fire a single electron at the slits, you see a single spot on a photographic film. That suggests that electrons are like isolated particles. A single electron, you get a single spot. But when thousands of electrons are fired at pairs of slits, you get thousands of separate spots, and they gradually merge into what looks like an interference pattern. The conclusion is that electrons must behave in some way both as particles and as waves. And at the atomic scale, we call this the wave-particle duality. This is behavior unlike anything we experience at the macroscopic scale of our daily events. Wave-particle duality brings us full circle to the Bohr atom and its strange non-accelerating electron orbits, those electrons that seem to be at discrete energy levels that just disappear from one and appear at the other but never are anywhere in between. Consider the stable electron orbits for a hydrogen atom, for example, that has one electron and one proton. Where can that electron be? What is the electron like? If you think of the electron as a particle, then Newton's equations for motion can be used to analyze possible orbits. That is, for a given energy, a given mv squared, which is the kinetic energy of the electron, how far out do you need to be in order to achieve a stable orbit, because you have a positive charge and a negative charge and therefore an attractive force. So you can analyze this just like a little Newtonian universe if you want to. If the planet's going to achieve a stable circular orbit, then the gravitational force pulling down the planet has to be exactly balanced, of course, by the gravity and the outward thrust. So this is a real analogy to a planetary system, even though we've seen the Bohr atom is not like a planetary system. So by the same token, if an electron is going to achieve a stable orbit, then you have to have this attractive electrostatic force balanced by the momentum of the electron. These calculations, by the way, lead to an infinite number of possible stable electron orbits, and you can catalog those down from the first orbit on up. Then now let's think about the electron in a completely different way. Let's think about the electron as a wave. When a wave is restricted to lie in a circle, it needs to adopt a pattern which is called a standing wave. You have to have an integral number of wave crests fitting into that circular orbit. This feature can be illustrated by a vibrating string, and I want to show you some of these stable orbits. If you can imagine this telephone cord being looped back on itself in a complete circle, you'll be able to sort of visualize what I'm talking about. You can have the ground state, which is just a simple wave of the lowest energy. You can then go to the first stable orbit, the first excited state. There it goes. You see it's a little bit faster, and it's divided into 2 units, and that fits perfectly in the same length cord. Then you can go to a third excited state. There, we're getting that one going. And maybe getting up to the 4th excited state if I work a little bit harder. You notice that each of these higher excited states requires more energy. Shorter wavelengths, higher energy, higher excited states. These nodes, these perfect harmonics of a vibrating string, correspond in a very simple way to the different orbits, the stable orbits of electrons in the Bohr atom. The ground state has 0 nodes. And you have 1 node, 2 node, 3 nodes, depending on how many vibrations fit into that circular pathway. If an electron is going to achieve a stable orbit, a stable standing wave, then the velocity of the wave has to balance the electrostatic force, and you have to have an integral number of wave crests both. There are once again an infinite number of solutions corresponding to the positive integers for a wave that's in a stable orbit around an atom. Now, as it turns out, the electron orbits of hydrogen atoms correspond to the solutions of 2 completely different equations, one for particle behavior and one for wave behavior. In fact, the Bohr orbits correspond exactly to the only possible solutions that are present both for electron if it's considered as a particle and for an electron if it's considered as a wave. Somehow the electron knows it has to have both of these attributes, and it chooses those orbits which fit both possible models. I want you to think about these results in terms of energy. Every electron orbit can be represented by an energy. In the particle formulation, this energy has the kinetic energy of a particle. Each orbit has a different energy, with orbits closer to the nucleus having lower energies because the charged particles are a lot closer together. In the wave formulation, the energy corresponds to the wave energy of the electron. The orbital energies, it turns out, are exactly the same. If you treat it as a particle, you treat it as a wave. The calculations show that the amount of energy these electrons have are exactly the same, and the increments of energy correspond exactly to the photons that are emitted when hydrogen electrons drop from one energy state to another. It all fits together so beautifully, but it requires you to think about this strange idea, wave-particle duality. Electrons, they're not particles, they're not waves. There's some strange beast that's a combination of both of these things. We don't live in the subatomic world, so I guess we shouldn't be surprised that the subatomic world is rather different than our intuition might have suggested. It all fits. It all makes a consistent picture, albeit a strange quantum mechanical picture. Let me summarize the key ideas of quantum mechanics. I've told you about 3 central ideas in this lecture. First, at the scale of the atom, all physical quantities come in discrete packets. These discrete packets are called quanta. Matter is quantized, energy is quantized, charge is quantized, and so forth and so on. Everything is quantized at the subatomic scale. Second, because of this quantization, you cannot possibly measure any property of matter at that subatomic scale without changing the thing you're measuring in the process. And this leads to the uncertainty principle, the idea that you cannot know everything there is to know about the subatomic world. And third, the behavior of electrons and other subatomic objects have aspects of both particles and of waves. There's a wave-particle duality. The quantum world is strange. It's different from anything we experience in the world of baseballs and of automobiles. The role of science, though, is to formulate ever more exact descriptions of the physical world and events in that world. Some situations, like the orbit of a planet, are amenable to exact mathematical descriptions. Other situations, like the flipping of a coin, are better described in terms of probabilities. The advantage of science is that it constrains us to describe the world as it really is, not as we would wish it to be, not as we intuit it to be. If our everyday metaphors fail in the description of the quantum world, well, then we're just going to have to go out and science will help us invent new metaphors. In the next lecture, we're going to continue our exploration of the subatomic world as I introduce the periodic table of the elements.